Welcome back, everyone. Today we're going to be talking about the normal distribution, one of the most important concepts and distributions in statistics. So here we have a frequency distribution then of over 4 million observations of birth weights of newborn babies in the United States in 1991. And you can see that these 4 million observations take on a really characteristic pattern that follows this bell-shaped distribution, where most of the observations are clustered around the middle. And as we get more extreme values, either in the positive or smaller direction, the frequency of those observations gets less and less and less. And this is a classic example then of what's referred to as the normal distribution. The normal distribution is a continuous probability distribution describing this bell-shaped curve. And it's a really important distribution in statistics because it's a good approximation to the distribution of many biological variables. The other really interesting thing about this distribution is it's described by only two variables, the mean and the standard deviation of the population. Now here we have the equation that describes the normal distribution, and it looks really quite complicated. We're simply reporting the frequency of each observation with value y by some complicated formula. Now, there are a lot of terms in this formula, but the only variables in this formula are the population mean, indicated by mu, and the population standard deviation, indicated by sigma. There are other terms in here, like the base of the natural logarithm e and the value pi, but these are constants. And so the only thing then that defines what our particular normal distribution is going to look like are these two measures of the population mean and the standard deviation. So here we have two normal distributions, one with a mean of 5 and a standard deviation of 4, and the other with a mean of -3 and a standard deviation of 1/2. You can see that the mean is what shifts the distribution left or right, and the standard deviation determines how much spread there is in that distribution. More spread in the distribution on the left, less spread in the distribution on the right. And so these two parameters then completely describe the shape of this line, where the exact values along these lines are defined by the equation that I just showed you on the previous slide. Now, there are a number of important properties of a normal distribution that are worth talking about. The first is that it's a continuous distribution, not a discrete distribution. So we're not talking about the heights of bars. Instead, we're talking about the location and shape of this line. And so when we want to calculate a probability from this normal distribution, we need to be considering the area under the line rather than the height of a single bar with some known width. And that's because it's a continuous distribution rather than the discrete distributions that we've been dealing with so far. The second important property of a normal distribution is that it's symmetrical around the mean. And what I mean by that is that the lower half of the distribution is simply a mirror image of the upper half of the distribution. Or to think of it a different way, the way in which this line declines is exactly identical to the way in which this line declines. In addition, the normal distribution has only a single mode. Finally, the probability density is highest at the mean value. And what I mean by this is that the most common observation is the mean of the population. And so in this distribution then, the mean, the median, and the mode are all equal to one another. Now, there are other properties of the normal distribution that determine its bell-like shape. The first is that about 95% of the distribution lies within two standard deviations of the mean. So 95% of the observations are going to fall in between mu minus 2 standard deviations and mu plus 2 standard deviations. Now I said about because technically it's within 1.96 standard deviations of the mean, but in most cases we tend to just think of it as 2 standard deviations away from the mean in the positive or negative direction. The other defining feature then of the shape of this distribution is that about 2/3 of the observations fall within 1 standard deviation of the mean. And these two characteristics then are what determines this bell shape that is characteristic of the normal distribution. Now, I mentioned that a normal distribution is characterized by its mean and its standard deviation. But there is one normal distribution that's particularly interesting and important, and that's called the standard normal distribution. The standard normal distribution then is just a normal distribution that has a mean of 0 and a standard deviation of 1. Values in this standard normal distribution along this x-axis are referred to as z-scores. And we can take any observation on any scale and convert it to z-scores by taking that observation, subtracting the mean value, and dividing by the standard deviation of the population. So we can convert any normal distribution into a standard normal distribution by converting observations from their original scale into this score of z-scores. Now, just like with the probability distributions that we've talked about in the past, we can use a normal distribution to calculate the probability of getting a random draw from our distribution based on an observed value. So for example, in the standard normal distribution, where we're talking about z-scores then, we can calculate the probability of getting a value equal to or greater than 1.96 by calculating the area under the curve of this standard normal distribution. And this is what allows us to calculate a p-value from a distribution like this. The p-value just representing the probability of getting a value as extreme or more extreme than our observed value. So our z-scores then tell us how many standard deviations away from the population mean a particular value is. The probability of getting a value greater than that observed value then is the same as the probability of getting a value greater than the corresponding z-score from a standard normal distribution. So by this, I simply mean that the probability of observing a particular value doesn't change when we change from the original scale of the observations to this new z-score from a standard normal distribution. But in many cases, we find it easier to perform some of our calculations when we convert to this standard normal distribution. So let's work through an example then. Let's say the British spy agency MI5 determines that men that are too tall are more noticeable and don't make for good spies. As a result, they might implement a rule that says that a man must be shorter than 180.3 centimeters in order to qualify as a spy. Now we know that the mean height of British men is 177 centimeters, and the standard deviation of height in British men is 7.1 centimeters, and that heights in men follow a normal distribution. So with all of this information then, we can calculate what proportion of British men would be excluded from being a spy because of this height criterion. So how might we do this? Well, we know that the mean height of British men is 177 centimeters. The standard deviation of height is 7.1 centimeters. And this observation, this threshold that we want to explore, is 180.3 centimeters. So what we want to determine then is what the probability is of a British man having a height greater than 180.3 centimeters. Now, to calculate this, we're going to convert our heights from the original scale into these z-scores by taking our observation, subtracting the mean, and dividing by the standard deviation. And from this, we can take our threshold of 180.3 centimeters and convert this to a z-score of 0.46. So a height of 180.3 centimeters then is 0.46 standard deviations above the mean. We can then compare this z-score to our standard normal distribution of z-scores to see where in the distribution this value of 0.46 falls. And we can see that a good proportion of the distribution falls to the right of this value. And what that means then is that a decent proportion of British men, in fact, are greater than 180.3 centimeters tall and would be excluded from being spies in MI5. Now, to calculate the exact probability or proportion or area underneath the curve shown in red, we can use a little bit of code in R using the p-norm function where we specify our z-score and that we do not want to consider the lower tail of the distribution down here. Instead, we want to consider the upper tail. And we can calculate then, or let R calculate for us, that the proportion of British men greater than 180.3 centimeters is 0.323. So about 32% of the male British population would be excluded from being spies in MI5. So before we go too much further, let's pause and remember some of our rules about doing math with probabilities when events are mutually exclusive. Here we have in red the probability of the British man being greater than 180.3 centimeters. Now remember that all of our probabilities, our entire population, needs to sum to 1. So the probability of being greater than 180 centimeters and the probability of being less than 180 centimeters need to sum to 1. So the area under the curve shown in red and the area under the curve shown in gray must together sum to 1 to account for all of the observations and their probabilities. So if we were instead interested in calculating the probability of being less than this threshold, the area shown in gray, we could simply rearrange this equation and say that the area shown in gray is simply equal to 1 minus the probability of being greater than 180 centimeters. As we calculated before that the probability of British men being greater than 180 centimeters is about 0.323. And as a result, the probability of being less than this height threshold must be 0.677. Now, what if MI5 also excluded men who were too short? Let's say they imposed another threshold or a lower threshold of 167 centimeters. So in this case, we could calculate what proportion of British men would be excluded from joining MI5 because their height was less than this threshold of 167 centimeters. Well, to do this, we could convert 167 centimeters into a z-score by taking 167 minus the population mean divided by the standard deviation to calculate a z-score of negative 1.4. We could then determine what proportion of the population following a standard normal distribution falls below this z-score of negative 1.4. And we can calculate this using the p-norm function in R again to determine that 8% of the standard normal distribution falls below negative 1.4. So about 8% of the British male population would be excluded from joining MI5 if they were to have this height threshold. Now, what if we combined these together and we tried to determine what proportion of British men would be excluded by these two height thresholds, both the upper threshold and the lower threshold? Well, to do this, we would need to calculate the probability of being taller than 180.3 centimeters, together with the probability of being shorter than 167 centimeters. And we would simply then add those two probabilities together. And that corresponds to the area in blue plus the area in red. And we can do this again using our R code with the p-norm function to sum together these two probabilities, and we would calculate that about 40% of the British male population would be excluded by these two height thresholds. And if you remember that our probabilities must always sum to 1 across all of the different scenarios that we're talking about, if 40% of British men would be excluded, then we know that 60% of British men would be included or would be candidates for MI5 with these two height thresholds. Now, some sharp observers looking carefully at this standard normal distribution on the right might begin to get a little bit worried about our British spies, wondering if perhaps they might in fact be double agents for the French government. Now, we've talked about the normal distribution and why it's a convenient distribution for being able to calculate probabilities based on information about only the population mean and standard deviation. But in addition to being really well defined, the normal distribution is called the normal distribution because it's everywhere. A really wide range of variables tend to fall in this characteristic bell-shaped pattern. So if we look at an empirical distribution of body temperature or brain size or the number of bristles on the abdomen of fruit flies, we find that they all tend to follow this characteristic pattern that is really well fitted by a normal distribution shown in black here. So why is the normal distribution so common? The reason for this is because of what's called the central limit theorem. And the central limit theorem states that the sum or mean of measurements from a normal distribution will themselves be normally distributed. So if you take a bunch of variables that are normally distributed and you add them together or you average them, then the end result of this calculation is going to be a normal distribution. But in addition to that basic principle, the sum or mean of measurements from distributions that aren't normally distributed will also tend to be normally distributed if observations are sampled randomly and if the sample size is large enough. And so the reason that many biological measurements are normally distributed is because most of those measurements arise from underlying processes that tend to add together or average across one another to determine the final measurement that we are considering. So let's work through some data then as an example of the central limit theorem. The distribution on the left represents the age at death of about 75,000 humans in Switzerland during 1918 when the Spanish flu epidemic was going on. Now, Spanish flu impacted disproportionately the young, which is the reason for this very large spike in deaths among young people. But you can see that this distribution is very clearly not normally distributed. There are three distinct modes, and it's not at all symmetrical. But if we sample from this distribution and we collect a random sample of even 2 observations, we get a sampling distribution that itself is starting to look kind of normal. If we sample only a single observation, then our sampling distribution just recreates the original observations. But as soon as we increase our sample size to 2, we're starting to get now a sampling distribution where each value represents the mean of these 2 observations randomly pulled from this distribution. And we're starting to get kind of a normal-like sampling distribution. As soon as we get up to 4 observations per sample, we can start to see that the sampling distribution is getting much more normal. And by the time we get to a sample size of 64, we're getting a sampling distribution from this highly non-normal variable that itself is really normally distributed. And so it's really important to pause for a moment and think about this hugely important principle. Many of our statistical methods assume that the distribution of sampling means is normally distributed. But here we've just shown that even if the underlying data are not normally distributed, the sampling means themselves will be normally distributed as long as the samples are drawn randomly and the sample size is reasonably large. And once this is the case, then we can leverage some of the important statistical tools that rely on the probabilities that come from this normal distribution, even if the underlying data themselves are not normally distributed. So here we've talked then about the normal distribution, which is our first example of a continuous distribution that can be defined by only 2 parameters, the population mean and the standard deviation. The normal distribution is an extremely important distribution in statistics because it's extremely common and really useful for calculating probabilities. The reason the normal distribution is common in biology is because most things are made up of component parts that tend to add together. And when we add together or sum or average across even variables that are not normally distributed, the sum or mean of those values will itself tend to be normally distributed. And as a result, we get this tendency towards things moving towards normal distributions. One particular normal distribution that is important for performing some of our calculations is what's referred to as the standard normal distribution, where the mean is equal to 0 and the standard deviation is equal to 1. And we can convert any observation from any normal distribution into a standard normal z-score by subtracting the population mean and dividing by the standard deviation. So I hope this video has provided you then with a bit of insight into what the normal distribution is and why it's such an important distribution in statistics.